In today's session, we will discuss some of the most important and frequently asked questions on the BJT and associated circuits like biasing techniques, common emitter, common base configurations, and amplifier analysis. All these question models are based on the previous year examinations of GATE, IES, ISRO, DRDO, Polytechnic Lecturers, and other state public sector unit examinations. Let's welcome to the channel Electronics Pariksha. Now let's see the first question. In the BJT amplifier shown in the figure is a transistor biased in the forward active region putting a capacitor across RE will. So here in the circuit there is no capacitor across the emitter resistance. So if we place a capacitor across the emitter resistance, that is CE, what is going to happen? What will happen to the voltage gain? And what will happen to the input impedance? This is what the question is. This question is asked in GATE 1997. If you see the second question, this is also a similar question. Okay, here he is asking what will happen if the capacitor resistance is removed. If CE is removed, what will happen to input impedance and voltage gain? So now let's see, these both questions are similar. We'll see the difference. Okay, now in the we have two cases. One is the circuit with emitter capacitor, the other one is circuit without emitter capacitor. Now let's draw and check the differences. This is a simple circuit I'm drawing. Common emitter configuration, where this is the emitter model resistance, small emitter model resistance, which is negligible, and there is emitter capacitor, capital, emitter resistor, capital RE. Okay, this is collector, this is base, and there is a collector resistance RC, across which the output is taken. This is the basic circuit. This is when CE is not there. CE not available. So whenever the emitter capacitor is not available, we have to consider the emitter resistor. Now second case, we will see the circuit. This is the transistor circuit. This is the emitter model resistor. This is emitter resistor. Across this, there is the emitter capacitor also. Okay, so when emitter capacitor is there, this emitter capacitor will bypass this emitter resistor. So we have to draw this as a short circuit. This emitter resistor will not be there in the AC load line analysis. Only emitter model resistor will be there, and as usual there will be collector resistor RC as a load resistor across which the output is collected. This is base, this is collector, and this is emitter. Now let's analyze the circuit. If you apply the Kirchhoff voltage law in the input loop, what will happen? By KVL at the input loop, the base voltage VB is equals to, this is the base voltage VB is equals to the current, emitter current, that is flowing through emitter model resistor, plus emitter current IE, that is flowing through emitter resistance. Now VB is equals to this emitter current, I can write it as 1 plus beta into IB multiplied by RE dash plus capital RE. So the input impedance is equals to input voltage, base voltage, divided by input current IB. This 1 plus beta I am writing as beta into RE dash plus capital RE is the input impedance. In this case, voltage gain AV is equals to output voltage divided by input voltage. Output voltage is the output current, collector current, multiplied by load resistance, that is collector resistance in this case, divided by input current IB multiplied by input resistance, that is beta RE dash plus capital RE. So now IC by IB can be written as current gain, that is beta. Okay, IC by IB is nothing but the current gain beta. Beta gets cancelled. The voltage gain can be written as RC divided by small RE dash plus capital RE. This is the voltage gain when emitter capacitor is not available. In the second case, we'll see Apply the Kirchhoff voltage law in the input loop. This is the base voltage. Here VB is equals to IE multiplied by emitter model resistance, which can also be written as 1 plus beta into IB RE dash. So the input impedance is equals to VB input voltage, base voltage divided by base current. So this 1 plus beta, I am writing it as beta, approximate value. So beta into RE dash. So now the voltage gain AV is equals to output voltage divided by input voltage. The output voltage is a collector current multiplied by collector resistance. Input voltage is input current, that is base current, multiplied by input impedance. IC by IB can be written as beta current gain. Beta beta gets cancelled. So the voltage gain is RC divided by small RE dash. Now you observe these values. This is the input impedance when emitter capacitance is not there. This is the input impedance when emitter capacitor is available. So if you place the capacitor, input impedance reduces. If you remove the emitter capacitance, input impedance increases. Very simple. Similarly, the voltage gain, if you observe, if you place the capacitor, emitter capacitor, the voltage gain increases. If you remove the capacitor, the voltage gain reduces. Okay, now we'll answer this. The first question he is asking, what happens if you place the capacitor across RE? He is telling we have to place the capacitor. If you place the capacitor, conditions are this: input impedance decreases and voltage gain increases. Voltage gain increases and input impedance decreases. Answer is option B. For the second question, if CE is removed, input impedance increases and voltage gain decreases. Answer is option J. Okay. Hope this is clear. Like the video, share the video, and subscribe to the channel for better content and more videos. For the amplifier circuit of the figure, the transistor has beta of 800. The mid-band voltage gain of the circuit will be. If you observe carefully, input is at the base. This is collector and output is taken across the emitter. As output is taken across the emitter, this is a common collector configuration. So in the common collector configuration, the voltage gain will be approximately equal to unity. The voltage gain AV is approximately closer to 1. We'll just draw the circuit and see the equivalent circuit. This is the equivalent circuit. The 100 kilo ohms and 200 kilo ohms come in parallel in the AC load line analysis. So there will be a small input resistance, emitter model resistance here. This is RE dash, and this this is the 470 ohms emitter resistance. The output is collected across the emitter resistance. This is the output. Now the voltage gain AV is equals to output voltage divided by input voltage. The output voltage I am noting it as V0, whereas the input voltage will be VBE plus V0. Okay, input voltage will be VBE plus V0. This is the base current, and this is small resistance, emitter model resistance. So VBE is very very small. We can neglect that. V0 divided by V0. This will be approximately closer to 1. The voltage gain of the emitter follower configuration, this is also called as emitter follower. Emitter follower is approximately equal to 1. Okay. If you do not understand this, I will tell you in a very simple way. See, this is the base, this is the collector, this is emitter in our normal rotation. This is emitter resistance, this is collector RC, and here VCC is given. So this is the input voltage, base voltage. This is the emitter voltage, that is output voltage. You please apply the Kirchhoff voltage law in the input loop. What you will get, the base voltage is equals to the base emitter voltage VBE plus emitter voltage. Okay. Here the base VBE, which is equal to 0.7 volts, very very small voltage, so it can be neglected. This can be neglected to 0. So 0 plus VE emitter voltage. This emitter voltage itself is the output voltage. Okay. That emitter voltage itself is the output voltage. like this. So now the input base voltage is equals to output voltage. So now the voltage gain will be output voltage is equals to input voltage. Both are same. It will be closer to 1. This is the simplest way to analyze the emitter follower circuit. So now the answer is option C. We'll see the next question. In the amplifier circuit shown in the below figure, the values of R1 and R2 are such that the transistor is operating in 3 volts and IC is equals to 1.5 milliamps when beta is 150. So this is the Q point. I am writing this as Q point 1, whose VCE and IC values are given as 3 volts and 1.5 milliamps when the beta of the transistor, beta, that is beta 1, is 150. So now for the transistor with beta is equals to 200, what happens to the new Q point? So he's asking to find out new Q point, that is Q2, VCE and IC values if the beta of the transistor is 200. So beta 2 is 200. Okay. Now let's find out this. You just apply the Kirchhoff voltage law in the output loop here. Now we are calculating for the transistor whose value is 150. Okay, case 1 we are calculating. In case 1 he has already given the IC value and the VCE value. So I'm applying Kirchhoff voltage law in the output loop by KVL in output loop. I will get VCC is equals to ICRC plus VCE. So VCC is 6 volts, collector current is given as 1.5 milliamps multiplied by collector resistance is not known to us, which is R2. VCE is 3 volts. So by calculating this, R2 will be equal to 2 kilo ohms. Okay, R2 is equals to 2 kilo ohms. We got it. Next thing, I would like to find out the base current here. So now the base current IB is equals to IC divided by beta. IC is 1.5 milliamps, beta value is 150, beta 1. So now the base current is equals to, the base current is 10 microamperes. So now the base current remains same here because the base current depends on R1. R1 is a fixed value. It doesn't change. He is telling only transistor I am changing with the beta 1 of 150 to beta 2 of 200. So now the transistor is replaced. So if the transistor is replaced, what will be the new collector current? IC2. New collector current is beta 2 into IB. The base current remains same. So the beta 2 is 200. The base current is 10 microamperes. So the new collector current is equals to 2 milliamps. So new collector current is equals to 2 milliamps. This value is found. This is 2 milliamps. Now we need to find out VCE. VCE2 is equals to VCC minus IC2 into R2. So VCE new VCE value is equals to, the VCC is 6 volts minus 2 milliamps multiplied by the collector resistance is 2 kilo ohms. So this will be equal to 2 volts. So the new Q point is 2 volts and 2 milliamps. So the answer is option A. We'll see the next question. If the transistor in the figure is in saturation, the collector current is always equals to beta DCIB equal to minus beta DCIB greater than or equal to beta DCIB. IC is less than or equal to beta DCIB. We'll see this in great detail. Okay. So now for the transistor to be in saturation, we have already discussed this concept in the previous videos many times. To be in saturation mode, the collector current, expected value of collector current must be greater than or equal to collector saturation current. Okay. So the collector current expected value should be greater than or equal to collector saturation current. So now this collector current can be written as beta DC into IB. Collector current formula itself is beta into IB. So this I am writing as beta into IB greater than or equal to IC saturation. So if you observe carefully here, the collector current is less than or equal to beta DC into IB. Like the video, share the video, and subscribe to the channel for better content and more videos. The IC saturation is less than or equal to beta DC IB. So the answer is option D. So how to find out this IC saturation and beta DC IB? This you have to find by applying the KVL at the input loop. By applying KVL at the input loop. Okay. That is VBB is equals to the base emitter voltage VBE plus VE, that is emitter current and emitter resistance. So that you can find out the emitter current, from that you can find out the base current also. This is the way how to find. How to find the collector saturation current? The answer is simple. The VCE collector saturation current, you have to apply the Kirchhoff voltage law in the output loop by applying KVL at the output loop. You will get VCC is equals to VCE saturation plus IC RC. Here IC is IC saturation. So IC saturation is equals to VCC minus VC saturation divided by RC. This is the way how you have to calculate IC saturation and beta DC IB. You have to compare these values. Okay. We'll see the next question. In the circuit of the figure, assume that the transistor is in active region. He is telling the transistor is working in active region. It has a large beta. The large beta means you must understand that IB is very, very less, negligible. The base current is negligible. And the collector current is approximately equal to emitter current. And its base emitter voltage is 0.7. Okay. The VB is equals to 0.7. The value of IC is, he's asking us to find the value of collector current. Fine. First, we will find out the voltage across this 5 kilo ohm resistor. This is nothing but a base voltage VB. So here VB, voltage across 5 kilo ohm resistor, is VCC divided by R1 plus R2 multiplied by R2. So VB is equals to, VCC is 15 volts, R1 plus R2 is 15 kilo ohms multiplied by 5 kilo ohms. So the base voltage is 5 volts. So the base voltage is 5 volts. This is equals to 5 volts. Now we apply the Kirchhoff voltage law in the input loop. By applying KVL at the input loop, you will get VB is equals to VBE, base emitter voltage, plus VE, emitter voltage, voltage across the emitter resistance, which can also be written as emitter current multiplied by emitter resistance. So VB is equals to, VBE is 0.7 volts, emitter current is IE, and emitter resistance is 430. Now the base voltage is 5 volts. You substitute that here. Then emitter current you will get as emitter current IE. You will get as 10 milliamps. Now the emitter current is nothing but it will be same as collector current. So 10 milliamps. Answer is option D. We'll see the next question. In the differential amplifier of the figure, if the source resistance of the current source IEE is infinite, then the common mode gain is. He's telling the source resistance of this particular current source is infinite. So now we'll see what is common mode gain and differential mode gain. The differential mode gain for this transistor is differential mode gain is equals to GM, the transconductance, multiplied by the collector resistance. This is the basic formula. Whereas the common mode gain AC is equals to minus RC divided by 2 into RE. This RE is nothing but the emitter resistance here. This RE is nothing but emitter resistance. He is giving this as an infinite value. Emitter resistance is infinite. So if emitter resistance is infinite, the common mode gain will be 0. So if RE increases, emitter resistance increases, the common mode gain will reduce. The common mode rejection ratio CMRR is the ratio of common differential mode gain and common mode gain. So if common mode gain reduces, CMRR will increase. Okay, the common mode rejection ratio will increase. So now in the question he is asking, then if the source resistance, emitter resistance tends to infinity, then the common mode gain he is asking. The common mode gain is equals to 0. Answer is option A. Differential mode gain, it does not depend on emitter resistance, so it will be constant. The common mode rejection ratio will become infinite. Okay, right. We'll see the next question. The circuit of the figure is an example of feedback type. Which of the following? So we have got 4 types of feedback circuits. In that, we will see which type this belongs to. This is an amplifier. This is the output. This is the input. There will be a feedback circuit here. This is the feedback circuit. It can be a resistor, capacitor, or anything. This feedback circuit, actually, there in the output we have to collect a sample and feed it to the input. If you are collecting parallelly from the output, this is called parallel sampling. You are collecting it parallelly. How you are saying it is parallel? Because the current divides here. If the current is coming, it will divide here. So if there is a current division at the sampling part, then it is called as parallel sampling. This is called parallel sampling or voltage sampling. This is called voltage sampling. Always remember, if you are collecting this as a in parallel with the output where the current is divided, this is called as voltage sampling. Now, how you are feeding to the input? If you are feeding to the input in the same manner such that the current divides again. Even here, if you see, the current will come here. Here the junction forms. So there is a current division rule that applies here. So this is called as a shunt mixing. This is called as shunt mixing. When in this such kind of circuit is called as voltage shunt feedback. Voltage shunt feedback circuit. Here what happens? You are collecting the samples in a parallel way and giving it in a parallel way. So input impedance and output impedance both will reduce. Whenever there is a shunt sampling or shunt mixing, the impedance will reduce. Simple logic, when you put 2 resistors in a parallel way, what happens to the equivalent resistance? It will reduce. This is R1 and R2. When both are in parallel, the equivalent resistance will reduce. When the resistances are connected in series, the equivalent resistance will increase. Okay, see the same logic you apply here. You are taking the parallel sampling, so output impedance should reduces. Similarly, you are giving the parallel mixing, shunt mixing, so input impedance also reduces. Okay, so now if you see in the circuit, this is the feedback element. This feedback element is connected at the output such that current is divided here. Current will be divided here like this. So this is called shunt sampling or voltage sampling. Even at the input side, it is given in the shunt mixing. That's why this input current and this current, this will be current division rule will apply here. So this is voltage sampling and shunt mixing. So voltage shunt circuit. Sri Raghava Academy online coaching center for the regular and backlog students dedicated to diploma and engineering courses. Semester wise and subject wise coaching is available. Contact the number 70192 46753.